The General Principle of Relativity in its Philosophical and Historical Aspect, by Herbert Wildon Carr. Chapter 6. The Problem of Gravitation. It is a curious thing that Descartes, who proposed a new method of philosophy, the distinctive form of which is universal doubt, and the principle of which is that nothing must be accepted as true unless its evidence is presented to the mind with a clearness and distinctness which excludes doubt, should have worked out a hypothesis of the system of the universe, complete down to the minutest detail. There is no greater contrast in the history of Western intellectual development than his system presents to the method and philosophical system of Newton, which completely supplanted it. Newton's method was experiment, and his philosophy he described as the experimental philosophy. This does not mean that Newton himself was an experimentalist. Devising experiments in the manner of Galileo was not his distinctive work. He was a mathematician like Descartes, and all that he insisted on in his natural philosophy was that nothing should be accepted as true on the clearness and evidence of the pure idea, unless it had first been submitted to the test of positive experimental proof. It is also curious, in comparing these two great minds and the work they accomplished, to observe that while the speculative philosophy of Descartes has secured a permanent place in literature, his physical system, which was the supremely important thing to his contemporaries and his successors, is entirely rejected, and studied only, if it is studied, for its antiquarian interest. Newton, on the other hand, who was equally famous to his contemporaries and immediate successors as a speculative philosopher, is now remembered as a great mathematician and as the discoverer of the universal law of gravitation, while his philosophy is entirely neglected. Even our knowledge of his great discovery is not first-hand. The Philosophiae Naturalis Principia Mathematica is not a classical work of philosophy like Hobbes's Leviathan, Locke's Essay on the Human Understanding, Spinoza's Ethics, and the other great works of his contemporaries. It is a concealed book for all but advanced mathematicians, and our knowledge of Newton's discovery is enshrined in a moral tale concerning his reflection on the fall of the apple. It is strange there should be so little direct study of the work of one of the greatest geniuses our country has produced. It is further of interest to note that though Newton in his lifetime won immediate and unquestioned recognition, he was elected President of the Royal Society 25 years in succession, his views never obtained wide or important acceptance. It was after his death, 1727, and in consequence of the publication of Voltaire's Éléments de la philosophie de Newton in 1738, and the translation of the Principia Philosophiae into French some years later, that Newton's philosophy triumphantly disposed the Cartesian vortex theory and became the accepted basis of physical science. Newton was born in 1642 and was therefore 8 years old when Descartes died, and his years of study and research were those during which the Cartesian system reigned unchallenged. The Principia Philosophiae, the work of many years, written in Latin and bearing the same title as Descartes' famous work, was published in 1886-7. It presented his theory of gravitation and his formula of the universal law. The famous story that this was a sudden discovery following a meditation set going by seeing an apple fall in the orchard of Woolsthorpe from a tree which was shown to visitors for about a century and which after he had fallen through decay was carved up into souvenirs, is generally rejected as legendary and mythical. Certainly if we suppose, as is usually implied, that Newton at the time was of a poetical and impressionable turn of mind, and awakened by a simple occurrence to the thought of the mystery underlying natural processes, nothing can well be more improbable than the story. When, however, we take the anecdote in its historical setting, we see at once that, whether it be legendary or not, something very like it must have happened. What is certain is that the circumstance, falling apple or whatever it may have been, did not originate the meditation, but broke in upon it. The authority for the story is Voltaire, who had heard it from Mrs. Conduit, a niece of Newton, wife of a Fellow of the Royal Society who was one of Voltaire's intimate friends. The story is: one day in the year 1666, Newton, in the retirement of the country, he had withdrawn from Cambridge to Woolsthorpe on account of the plague, seeing the fruit falling from a tree in the orchard, according to the story which his niece Mrs. Conduit told me, fell into a deep meditation as to the cause which thus draws all bodies in a line which if prolonged would pass almost through the earth's centre. What, he asked himself, is this force? It acts on all bodies in proportion to their mass and not to their surfaces. It would act on this fruit now falling from this tree were it so removed that it had 3,000 or 10,000 fathoms to fall. If this be so, then this force must be acting from where the moon is right to the center of the earth. If so, then, whatever this power be, is it not the same as that which keeps the planets moving round the sun and the satellites of Jupiter in their orbit round that planet? Now it has been shown by the inferences drawn from Kepler's laws that these secondary planets are weighted towards the center of their orbits, more in proportion as they are near, less in proportion as they are distant, that is reciprocally according to the square of their distances. A body in the moon's position and a body close to the earth must both weigh on the earth in exact accordance with that law. This story shows clearly the subject of Newton's meditation. He was pondering over Descartes' system of celestial movement. But why should that be disturbed by the falling apple? It flashed across him that here was a phenomenon in flagrant violation of Descartes' vortex principle. By every reason alleged by Descartes, the apple ought to have flown upward and outward, and not to have fallen downward. The centrifugal force of a vortex causes the heavy body held by it, when released, to leave it at right angles to the axis of rotation, as when, for example, the stone in a sling is released. This at once brings to mind the laws of Kepler, in particular the third law, that the cube of the distance of each planet from the Sun is proportional to the square of its time of revolution. But what strikes Newton is that weight must be determined by mass and distance, and not, as Descartes' principle required, by surfaces in changing relations consequent on movement. It is quite certain, therefore, that if it was not a falling apple, it was some analogous circumstance which originated in Newton's mind the doubt concerning Descartes' principle, and led to the formulation of the new law, and to the return to the concept of absolute space and time as the basis and framework of the physical universe. To make this clearer, it will be well to look a little closely at the way in which Descartes conceived the vortex to have worked in bringing about the distribution of matter in the solar system. In rejecting the concept of atoms and the void, Descartes had no need to endow matter with weight as an essential attribute. As there is no void, and therefore no distinction between space and matter, that is to say, as matter is not conceived as in space or space as containing matter, the one and only essence of matter is extension. Without movement, this is pure homogeneity. If we conceive matter at rest, we must of necessity conceive its parts. If it consists of separate parts uniform in character, as regular figures such as cubes or hexagons, for only such will fit together to compose a plenum. Suppose now that movement is originated. It must, on the theory, involve relative change throughout the mass, and the effect must be that the shape of the figures will alter and continue to alter till they become entirely spherical. The more and the finer the spheres become, the more easily will they pass one another in moving, and their velocity will tend to increase continually. there will eventually be formed very minute and perfectly spherical particles, a very fine dust through which the particles will cleave an easy way, and denser particles, which will be driven outwards and form a dust on the circumference of the vortex sphere. This, according to Descartes' natural history of the world, is what has actually happened in our system. The fine spherical matter has collected at the center. It is the luminous or fire element and composes the sun. The finer dust fills the firmament and is the air element or transparent matter. Lastly, there is opaque matter which composes the crust of the earth. The place of this matter is somewhat unsatisfactorily explained in the system of Descartes. He suggests that the sunspots are a kind of scum which collects on the surface of the mass of spherical matter, forming the denser masses which are thrown off and become celestial bodies traveling in a straight line until they are captured by some vortex into which they enter. He supposes that our planets may have come from other systems and been caught up in the solar vortex. And he also supposes that the Earth is itself a vortex within the solar vortex with a similar structure, the fire element at its center, the air element surrounding this, and the opaque crust on the circumference. The obvious difficulty of this theory, which Descartes never saw, and which is only obvious to us since Newton's discovery, is that according to it, the heavier the matter on the circumference, the greater should be its tendency to obey centrifugal force and fly off. Descartes' theory, therefore, offered an explanation why the planets do not fall into the sun, but it had no explanation to offer as to why they keep a constant position in the solar vortex. It could explain why movement is centrifugal or centripetal at the equator, not why it is radial to the center from every point on the circumference. And lastly, it made no attempt to explain the behavior of heavy objects on the surface of the globe. Let us now turn to Newton's theory of gravitation. There is an active power which impresses on all bodies a tendency to move towards one another. In the celestial bodies, this power acts in inverse ratio of the squares of the distances of the centers of the masses and in direct ratio of the masses. The power is called attraction when we refer to the center, gravitation when we refer to the bodies which fall to the center. It is this power which causes bodies, liberated on the surface of the earth, to fall to the earth in a direct line to the center. The same force probably acts on the light emitted by luminous bodies, but we are ignorant in what proportion and have no means of discovering. It was not, however, till long after Newton had conceived the idea that he was able to confirm the theory and formulate the universal law. The account of his difficulties, which Voltaire has given us, is of special interest for the light it throws on his character as well as on his method. To determine the amount of the attraction of the Earth on the Moon, he must know the radius of the Earth and the distance of the Moon. Here is Voltaire's account. Newton was at a disadvantage that the only data he possessed on which to base his measurement of the Earth were the faulty calculations of English pilots who reckoned 60 English miles to a degree of latitude, the true amount being more nearly 70. And yet there had been a more correct measurement of the Earth. An English mathematician, Norwood, had in 1636 measured fairly accurately a degree of the meridian and had discovered it to be about 70 miles. But although this measurement had been made 30 years before, it was unknown to Newton. The civil wars which had afflicted England, always as disastrous for science as for general prosperity, had buried in oblivion the only exact measurement of the Earth which then existed, and there was nothing available but the vague estimate of the pilots. Employing this measurement, it was found that the Moon was too near the Earth, and the expected equations did not come out right. Newton did not try to supplement his theory by forcing nature to accord with his ideas. He gave up his great discovery, notwithstanding that the analogy with the other stars had appeared to make it so probable and though it seemed to come so little short of demonstration. This example of good faith alone deserves to give great weight to his opinions. Later on, more exact measurements were made in France, giving 25 leagues as a degree of the Earth. This gave the distance of the Moon as 60 radii of the Earth, and was exactly what was required to give Newton the demonstration of his theory. Newton's theory is that the Moon is traveling by its own inertia in a straight line and at the same time being attracted by the force of gravity towards the Earth's center, the influence being mutual, the composition of the forces giving the Moon's orbit. By applying Kepler's formula, he could calculate the exact amount of the gravitational force, or the weight of the Moon on the Earth at its distance from the Earth's center. Why was this theory unacceptable to the Cartesians? The main reason is clear. It proposed the very thing which to their principle was most abhorrent. Gravitation was an occult influence, and the Cartesians would accept no explanation which was not wholly intelligible and explicable by the aid of simple mechanics. Further, it raised the whole problem of action at a distance. According to the Cartesians, a body might exercise pressure on another body, and in fact this was a constant phenomenon, but in every case the propagation was instantaneous by reason of the continuity of matter in the vortex. The bell rings at the same moment at which the cord is pulled. In this way, the Cartesians explained how the Sun, though distant, could be the source of the sensation of light. No emanation passes from the Sun to our organs of sight, but a pressure is exerted and propagated through the transparent matter of the firmament. In like manner, they explained the tides. The pressure of the Moon, propagated through the intervening medium, depresses the liquid element on the surface of the Earth, causing it to bulge in the tidal wave. Action at a distance was puzzling and even disconcerting to Newton, and although, if it take place in fact, it has to be accepted, on the principle that nothing is impossible to God, yet he inclined to the hypothesis that the space, in which the masses in the solar system move, is pervaded with a subtle substance, an ether, through which the influence of attraction and gravitation is conveyed. It will be seen then that Newton's discovery demanded a complete revision, not only of the special hypothesis of the Cartesian vortex, but of the whole philosophical concept on which the Cartesian mechanism was based. Attracting and gravitating masses, forces determined by the inverse ratio of the squares of the distances between the centers of the masses, were clearly incompatible with the concept of a material substance whose essence was extension alone, and whose form was determined by relative movement within a self-contained and self-sufficing system. The new system required a framework of absolute space and time, space which was independent of, and indifferent to, the masses acting on one another within it, and a time flowing indifferently to the changes which it measured. Newton therefore takes us back to the old atomic theory. He reaffirms the void and a matter which is atomic in the sense that it may be impressed with movement, for to deny the atom would be in effect, as we have seen, to deny the possibility of movement. But it is not a simple return. There is a notable advance in the fact that the theory of gravitation has completely overcome the ancient difficulty regarding absolute direction. The problem which exercised Democritus and produced Epicurus's arbitrary hypothesis of an inclination is replaced with this law of universal gravitation. The mysterious force of attraction, which observation and experiment have required us to accept, remains a mystery in natural philosophy. From the standpoint of physical science, the gain seems enormous. The whole scheme of the universe is simplified and settled on a basis of common sense. We are provided with absolute standards of reference and appear to have no obstruction to the unlimited advance, through experimentation, of exact knowledge. But the new concepts raised very serious difficulties in philosophy. To Newton himself, the materialism of his system presented no difficulty. He held firmly to the necessary existence of God, and the creation or annihilation of matter seemed to him to come easily within his conception of the power of God. The old difficulty of the atomists, that matter in its very concept was a necessary existence, and therefore eternal and indestructible, did not trouble him. It seems probable to me, he says, that God in the beginning formed matter in solid, massy, hard, impenetrable, movable particles, of such sizes and figures, and with such properties, and in such proportions to space, as most conducted to the end for which he formed them. But space and time themselves, what was their relation to God? All existence depends upon them, and they depend on nothing, and their non-existence is unthinkable. At the close of his questions in the Optics, he says, "Do not these phenomena of nature make it clear that there is a being incorporeal, living, omnipresent, who in infinite space as in his sensorium sees, discerns, and understands everything most intimately and with absolute perfection?" By the term sensorium, Newton expressed his idea of the relation of God to infinite space. God is not in space, and space does not contain God. It is part of God's nature. It was a difficult and ambiguous expression, and of course not allowed to go unchallenged. It was the subject of a correspondence between Leibniz and Newton's most famous disciple, Clark, in 1715–16, a correspondence which was only interrupted by Leibniz's death. What Newton intended by the doctrine was that allowing, as we must, for the impossibility of expressing God's nature in human terms, we have to admit that nothing can act, know, or see where it is not. And when therefore we affirm of God that He is omnipresent, we mean that He acts, knows, and sees at every point and in all points of space. Space, therefore, is God's sensorium. Leibniz criticized this as being tantamount to making God's relation to the world analogous to the relation of the soul to the body. The sensorium would then represent in God's nature what the pineal gland represented in human nature, in Descartes' theory of the relation of the soul to the body. The real difficulty for Newton was that however he might wish to conceive God's relation to nature, the absolute existence of space and time as physical realities was fundamental for his conception of gravitation as the attraction of masses. Space is not where God places masses, and time is not when God elects to create them, for then we should have to say that if God had chosen a different place or a different time for creation, the different places and times would have been not different but identical, and this involves absurdity. Physical science, however, has ignored these philosophical difficulties and framed its concepts on the supposition of absolute space and time, and this pure assumption has come to be a commonplace of everyday thought. The postulate of absolute space and even flowing time was not a speculative opinion of Newton. It was forced upon him by a scientific discovery, the discovery of the velocity of light. This discovery, as already noted, was made in 1675, just midway between Newton's first idea of a universal law of gravitation in 1666 and the publication of his Principia in 1686. It completely altered the whole problem of the measurement of celestial movements, for the time interval of light propagation must now enter into all the equations, and the date of any astronomical event can no longer be fixed by simple perception, it can only be known by calculation. As we are dependent on light signals, and these are subject to a time interval varying with the distance, how can there be astronomical science at all, except on the hypothesis of absolute space and time? It was a philosophical necessity, therefore, based on an experimental fact, which compelled Newton to postulate absolute space and time. In precisely the same way, it is a philosophical necessity based on an experimental fact, the Michelson-Morley discovery, which has compelled Einstein to reject the postulate and formulate in its stead the principle of relativity. To go back to the distinctive work of Newton and the formulation of the universal law of gravitation as a consequence of his discovery, great light is shed on his own conception of the nature of his work and on its relation to philosophical theory by the closing passage of the Principia Philosophiae, which I will quote. So far I have expounded the force of gravitation by celestial phenomena and by those of the sea, but I have in no way attempted to assign the cause. That force comes from a power which penetrates to the center of the sun and of the planets, without any diminution of activity, and it acts not in proportion to the quantity of the surfaces of the particles of matter, as mechanical causes do, but according to the quantity of solid matter, and its action extends on all sides to immense distances, diminishing always in exact ratio according to the square of the distances. I have not tried to deduce the cause of these properties of gravitation from the phenomena, and I make no hypotheses. For whatever is not deduced from phenomena is a hypothesis, and hypotheses, whether they are metaphysical or whether they are physical, whether they presuppose occult qualities or mechanical qualities, have no place in experimental philosophy. In this philosophy, propositions are deduced from phenomena, and general propositions are obtained by inference. Thus, the impenetrability, the mobility, and the impetus of bodies and the laws of their movements of gravity have been set down, and it is shown that gravity really exists, and that it acts according to the laws I have expounded, and that it applies to all movements of the celestial bodies and of our sea. It is not now possible to add anything concerning the very subtle spirit pervading heavenly bodies and latent in them, by whose force and actions the particles of bodies are mutually drawn together at minimal distances, and the contiguous cohere, and concerning electrical bodies acting at greater distances, now attracting, now repelling neighboring bodies, and how light is emitted, reflected, refracted, inflected, and also how it warms bodies, and how all sensation is excited, and how in animals the limbs are moved by volition, to wit, by the vibrations of the spirit propagated through the solid threads of the nerves from the external organs of sense to the brain, and from the brain to the muscles. These cannot be expounded in a few words, and at present there are not sufficient experiments by which to determine accurately and demonstrate the laws of action of this spirit.